All right, everyone. I'm going to go through a chapter 7 problem with a spring. This is from our learning problems, number 25. So here we go. Here we are putting ourselves in a position of an engineer. We're asked to design a spring that will give a satellite that has some mass. Oh, I guess we'll write this down. So we're given that the mass, I can't write. That the mass of the satellite is 11 to 60 kilograms, and that the velocity that we want this satellite to have, so we'll call that our final velocity, is 2.5 meters per second. And the spring can give a maximum acceleration, so we'll call this A max, and that has a value of 5g, where g is, oops, that's bad 5, where g is 9.8 meters per second squared. Okay, so those are our givens. The spring's mass, the recoil kinetic energy of the shuttle, and the change in the gravitational potential energy will all be negligible. So that means that our, well, it means a couple of things. So here's our satellite, or here's our shuttle, some big square. There's some spring attached to it that is attached to the satellite that is going to be going. So what's going to be happening is that this spring is going to recoil, and it's going to cause this satellite at this point to then have, oops, not at that point, sorry, I meant to put that on the other side, right here. So that is going to cause it to have this velocity v once we let it go. Initially, the velocity is 0, right, so it's being held in place, but our spring has been compressed some distance x. And so the couple of things that we want to find here that it's asking about is, for A, we want to know the K of the spring, what's its strength, and for B, we want to know how much that spring has to be compressed. All right, and the reason I'll do it here is because we'll be able to kind of, we're not going to solve them simultaneously, but steps that we're going to use are going to be, they're going to kind of overlap. All right. Well, anyway, we'll just state them here so we know what they are at first. Okay. So this recoil kinetic energy, which means, right, for every force there's an equal and opposite force, but it basically means that the velocity of the space shuttle feels as it recoils is essentially 0. It's negligible. So we don't have to worry about that. We also don't have to worry about any change in gravitational potential energy. So that's actually giving us another idea where this delta U grav is 0. So the change in that, is 0. And we don't care about the spring's mass. That's good. Okay, so we can do a couple of things here. So right off the bat, one of the easiest things that we can do and relate is energy conservation. Okay, so we're going to just start with that over here, just to make a note of it. So that we can use that, because we have that in our toolbox now. And that energy conservation means what? It means that our initial energy is going to equal our final energy. Excuse me, whatever energy we have to begin with is going to be equal to, maybe in a different form, but it's going to be equal to the same energy at the end. Okay. Oh, sorry. Now we also have this idea that the spring is going to cause an acceleration. Okay. Given that information, we also will want to use Newton's second law. Specifically, that the net force acting on some object is equal to the mass times the acceleration of that object. Okay. So let's actually start here. Okay. So if we draw a free body diagram of our object as it's in somewhere between the spring being released and when it leaves the spring, right? So while the spring is still attached, the satellite is experiencing a force from the spring in this direction, as I've drawn it here. Let's put in our coordinate system just to be consistent here, so we can keep that. Okay, and we're up in space, so we're not going to deal with any sort of gravitational, or not going to deal with any force from gravity. So we're up in space. That's not an important piece right now. But the important thing that we get from this free body diagram is that there's an acceleration that is being given by the spring, right? And we know that there's a maximum acceleration that we can have for this system. So the force that the spring is applying is the regular force of a spring. So, well, let's do this first. Let's write out our sums of forces in the x direction is equal to m times the acceleration in the x direction. And the force in the x direction is the force from the spring. And that is causing this acceleration. And we'll call it our max because that's what we want to find. That's the idea that we're using here. The force from the spring we know to be k times x, right? Depending on how much that coil is compressed gives us that force. And because we're looking for a maximum here, then we're going to be using that concept. So we end up with this relationship between our k, the x, the mass, and the acceleration. We are given these values, right? So we know the mass of the satellite, we know this acceleration, but we don't know k or x. So we need some way to correlate them together. So we're going to use energy conservation now. So our energy conservation, again, allows us to state that the initial energy is equal to the final energy. And we can write out our total mechanical energy, which is our motion, our kinetic energy, and our initial gravitational potential energy, our initial elastic or spring potential energy, it added to some other work, which in this case we don't have. There's nothing else going on, and so that's just zero. There's no friction, there's no other outside forces, so that's it. And that's all equal to our final energy, which is our kinetic energy plus our final gravitational potential energy and our final spring or elastic energy. Now we've already stated that change in our gravitational potential energy is zero. So these will also cancel out because we're given that this delta U grav is zero. And we know that it starts from rest, and so that this also goes to zero because our initial velocity is zero. So we have no motion. We can go on this right side now and look that the final spring potential energy is zero because it has now reached, sorry about that, because it has now reached its recoil position. So that goes to zero. So then we are just left with the idea, that all of the potential energy from the spring gets put into the motion, the kinetic energy of satellite. And so now we have yet another form that relates our k and our x to some values that we know. So if we simplify this just a little bit, right, we can cancel the half, and we're left with k x squared equals mv final squared. So now we have two equations. There's one here, there's one here, I guess we'll go through and do a check like we did before. We're given the mass. Oh, where did that pointer go? It's hard to see on here. We're given the mass. We're given the velocity. So again, the only things we don't know are k and x. So now we have two equations, two things we don't know. So now we can solve for one and put it into the other. Okay. So let's say that doesn't matter. It doesn't matter which one you solve for first. But let's because they did it in this order, let's solve for x in the first equation. So we get x is equal to 1 over k times m a max. Plug in to the second equation. So we get that k times this quantity, 1 over k m a max squared is equal to mv final squared. So that then we end up with k times 1 over k squared times m squared times a max squared is equal to mv final squared. So then this k cancels, one of the m's cancels, and if we bring the k to the other side, then we end up that with k is equal to m a squared max over the final squared. So now we have an equation that only has pieces that we know, right? We know m, we know a squared, or we know a max, and we know b squared. We can do a quick unit check. The units of k are newtons per meter. That's the units that we want them to be in. And that is equal to mass is kilograms, acceleration squared, right? So acceleration is meters per second squared. So we're going to have a square of all of that, and then a square of meters per second. So it's getting a little bit complicated here, but we'll figure it out. So we have meters squared per second to the fourth divided by meters squared per second squared, right? So now our meters cancel. Well, I don't know if we want to do the meters cancel because we want a newton. Oh, I have to be careful about this, right? So what's a newton? A newton here is, or how do we make a force? We make a force by multiplying a mass times an acceleration, right? But if we take, so yeah, that's what I was, well, let's not cancel those meters just because of the form that we want this to be in. We'll cancel one of them though. Cancel one of them. We cancel one of those m's, and then we will cancel two of these seconds. So that becomes a 2. Now we have kilogram meters per second squared, which is a newton, all over a meter, which is exactly what we have on the other side. So the units work out. That means that this equation gives us k, and that's great. So now we can use this k and plug this back in to solve for x. And we can do it in either of the equations. It doesn't matter. I'm trying to think which one would be best. Again, it doesn't, or easiest. Actually, doesn't matter. Okay, so let's just do it up here. This one. So now with k, we have that x is equal to m a max over k. So now we will plug in our k so that x is equal to m a max divided by m a max squared divided by v final squared, so that our masses can cancel, one of the accelerations can cancel, and this v squared comes up on top, so that we end up with x is equal to v final squared divided by ax. That's our equation for x. Again, if we want to do a unit check, x is in meters. Velocity squared is meters squared per second squared, and acceleration is meters per second squared. 1 meter cancels, the second squared cancels, and we end up with a meter, so that's good. Okay, so those are our two equations for the x and the k. So again, just to do a quick recap. Because we had enough information to talk about our acceleration, then we could use the second law to talk about the force creating this acceleration. We could use our energy conservation to give us a second relationship between our k spring constant and our x and known values. And then we have two equations and two unknowns. Solve for one of them, plug into the other, solve for that one, and plug into the other to get our two equations. And now we can just plug in our numbers and get some value. So I hope that was helpful, and look for some more problems coming up.